So, today, exercise 2G, derivatives of logarithms. So here we've got two rules, a little bit like yesterday. If we have y equals ln of x, then the derivative is 1 on x. If we have y is ln of some function of x, then the derivative is the derivative on the inside on top of the inside. Okay? So whatever the function is, you differentiate it, that goes to the top, and then the function goes to the bottom. We'll get into some examples straight away. So here I have y equals 3x times ln x. Alright, so we're looking, we can see we've got one thing times another. We know we need to use the product rule. So we're going to write out u and v, u dash, and then here we're onto something new. The derivative of ln x is 1 on x. So we recognise it's the product rule, we write out our u's and v's, differentiate u, no worries, differentiate v, here's our new skill, looks okay. Alright, let's make a statement, dy on dx, okay, they've given it to us in the form y, we're going to answer dy on dx, smash it together. U dash v plus uv dash. Okay, full marks there, although it can be simplified a little bit. Let's explain why. So we've got 3 ln x plus 3x times 1 on x. Whenever you have a number times a fraction, it's always going to the top. And the reason is, this number by itself is on top of 1. Okay? Anything by itself is always on top of 1, divided by 1. And when you're multiplying fractions, top times the top, bottom times the bottom, what would we be left with but 3x on top of x? And then you can see we've got x at the top and the bottom as a product can cancel. Alright, so our answer, if you were to simplify, is 3 ln x plus 3. Again, full marks here unless it specifically says rearrange it to be presented in this form. Okay, on to B. We have ln of, and then we have this function in here, 3x squared take 2x. We have ln of a function. So therefore, our derivative, we can jump straight to it. This is one step. Our derivative is the derivative of the inside. So when I differentiate what's on the inside, 3x squared, that's going to be 6x. Take 2x, that's going to be take 2. So the derivative on the inside of the inside on top of the inside. On top of 3x squared take 2x. Okay, so hopefully we can see the link there. Ln of f of x, the derivative of the function at the top, and then the function at the bottom. Alright, on to C. For C, we have e to the power of 3x take 2 multiplied by ln of x take 5. Alright, again, the multiplication means we're using the product rule. So we've got u is e to the 3x take 2. V, I'm going to express it like this. Alright, I'm going to express it like this. ln of x take 5 to the power of half. Because although we can differentiate the square root of x take, like we can treat it like that, it's much simpler for us to move the half out the front. Okay? And now we don't have a composite function there because the power is just a product out the front. And so all we're differentiating is this part. We don't have to worry about to the power of a half. You can still do it, but it will take you a fair bit longer. Alright, so in math we should always be looking for what's the simplest way, what's the simplest procedure. Okay, for u dash, alright, when we differentiate e to the f of x, it's going to be f dash of x, e to the f of x. So the derivative of 3x take 2 is going to be 3, and then we just have e to the 3x take 2. Alright, so that's what we did last lesson. So we've got u dash, we've got v, and we're ready to find v dash. Alright, again, this is going to be the easiest way to do it. The half is just going to hang out. Alright, the half is just hanging there, it's a product. And I've got ln of x take 5. So I'm saying, what's the derivative of x take 5? 1. all right, on top of x take 5. So that's what v dash is, and let's just smash all that together to get dy on dx. So u dash v plus u v dash. And that's it. All right, again, that one can be simplified a bit. You know, we could distribute that 2 at the bottom and so forth, bring the e to the top of the fraction, but let's just leave it and move on. Okay, D is going to be a nice one. We have the cubed root of ln of a function. So we've got 3 sort of things going on here. Firstly, the cubed root means it's a composite function. We've got the ln, and then we've got another function inside. So before we can differentiate this, we must first express everything as power, right? So I'm just going to restate it like this. Cubed root means to the power of a third. And then to differentiate it, we're going to use the chain rule. All right, we're looking in there, we're going, I have some function to the power of n. So my derivative then is going to be n f of x to the n take 1. All right, a third take away 1 minus 2/3. I'll stop there and I'll just give you guys a bit to catch up. Just get excited when it's lots of fun, ripping through it. Alright, so what have we done so far? We're recognising we've got this cube root. I need to express it as a power. Because of the power, that means I need to use the chain rule because we have some function to the power of n. Composite function, so chain rule. So I've gone n, f of x, n take 1. But the other part of the chain rule is you must multiply by the derivative. Okay, so we must multiply by what do we get when we differentiate this? Okay, so we're just focusing on the inside then, and we're looking at that and we're going, we've got ln of, again, some function. And so we're using our second rule. We have ln of some function. It's the derivative of that function at the top on top of that function at the bottom. So that's going to be 5x to the 4 take 2 at the top, on top of x to the 5 take 2x at the bottom. We'll wrap brackets around that. So that is that one, n f of x n take 1 times f dash of x. Very good. Okay, on to the last one then. We have differentiate ln of x to the 3 on top of x plus 2. Now, you might look at that and go, all right, I need to use the quotient rule first to find the derivative because we have u on top of v, and that would be an okay way of doing it, but it's going to take a long time. It's a faster way. Who can see it? Very good. We're going to separate the logarithms. So just recap here, laws of logs. We have ln a plus ln b, that's ln of a times b. We have ln of a take ln of b, that's ln of a on b. At the moment, we've got something like this. We've got ln of a on b, and so we can split it back in the opposite direction. We can say this function is equal to ln of x to the 3, take ln of x plus 2. Alright, that's what the function is equal to. This function and this function are the same. We haven't performed any differentiation yet. Alright, so the top one, take away the bottom one. And then we've even got this ln x to the 3. That 3 can rip out the front. You can differentiate, it's not going to matter, it's all going to end up the same. So I'll just restate it one more time. 3 ln x, take ln of x plus 2. Okay, we're ready to differentiate. We've got 3 times 1 on x. The 3 is just hanging out. The derivative of ln x is 1 on x. Take away. And when we differentiate ln of x plus 2, derivative of x plus 2 is 1 on top of x plus 2. Okay, so that's what we get when we differentiate it. That would be without simplifying. But here's a really good example of when you absolutely have to, because it says, it doesn't just say differentiate, it says show that the derivative can be manipulated and rearranged such that it ends up like this. So that means we've got a bit of work to do. We need to bring them together. We need to synthesize these two parts of the derivative. So now that we've written f of x, f dash of x, like we can just carry on the equals. The important part is to have the distinction between f of x and f dash of x, right? Once it's done, we're just following down the equals. So I've got 3 on x, take away 1 on top of x plus 2. And if I want to bring them together, I'm going to cross multiply the denominators, right? I need them to have the same denominator to make them, so I can add or subtract the fractions. So at the moment we have one fraction subtract another. If I want to bring them together, they need to have the same denominator. And so I'm going to multiply this one by x on top of x. Okay, I'm moving that denominator there, x on top of x. And I'm going to multiply this one by that denominator, x plus 2 on top of x plus 2. Now remember, we can do that because, well, x divided by x is 1. We're not changing its value. It's a legitimate operation. X plus 2 divided by x plus 2 is 1. We're not changing its value. And then hopefully you're looking and you're seeing that the denominator there is x times x plus 2, which is x squared plus 2x. That's what they have here. And the same over there, x times x plus 2. All right, so let's proceed with this one then. This 3 needs to distribute. So at the top there, we're going to have 3x plus 6 on top of x times x plus 2. Take away x on top of x times x plus 2. Now I'm keeping them separate just to really demonstrate they have the same denominator. It's clear. Let's bring them together. And that's what, 2x plus 6. All right, and this is maybe a good example to just bring up what we were talking about yesterday. We said yesterday, or when we had our last lesson, when is the function 0? If this is our derivative function, it's going to equal 0 when the top is 0, right? 2x plus 6 equals 0, x is minus 3. When x is minus 3, the slope, this is our slope function, the slope is 0. It's horizontal at that point. And then we've got, it's going to be undefined when the denominator is 0. What's that? 0 and square root 2. Negative root 2. Cool. All right, so that's enough to get started on derivatives of logarithms. I'll just talk about what else we've got. We've got some rearranging problems. So in the past, kids have said, oh, look, I've got the hang of the basic skills, but I want to practice this kind of thing where I have to rearrange it and bring it together. So there's some extra ones, all right? And they're not just all the quotient rule. You can see the first one involves product rule. The second one involves product rule, quotient rule, quotient. Yeah, so there's 3 product rule, 3 quotient rule. There's some more first principles problems there as well. I hope we're continuing to do them, all right? If not, here's a reminder. Time to start ticking that over in your brain. So yeah, so that's what we'll work on a bit today. Let's get started on it.